In this question, we're asked to analyze a situation where we have an object that's 1 centimeter in height and a given distance away from a screen. I'm just going to note this is our screen, and that's where we're going to produce the image. We were not told what the object is, so I drew a little tree, and I noted that it has a height of 1 centimeter. This whole diagram isn't going to be exactly to scale. However, you could do this through a very careful ray tracing. Alright, so what are we told? We're told that we have a diverging lens with a focal length of minus 20 centimeters. Okay, so I've labeled that diverging lens that I drew as 1, and I'm going to say, well, it's got an f1 that's equal to minus 20 centimeters. We're also told that that lens is 20 centimeters in front of the object. Okay, so let's make a note of that. That's important. So we have a distance, and that's going to be our S, our distance to the object, to the lens, and that's 20 centimeters. And I'm going to label this as 1 because we have more than one lens in this system. Okay. Now we're also told, okay, what is the focal length and the distance from the screen of a second lens? Now, we're not told what type of lens this is, but we are told that this combination of two lenses will produce a well-focused 2 centimeter tall image on the screen. So what does that tell us about this second lens? Well, let's imagine we had another diverging lens. What would happen? Well, we definitely would not produce an image on the screen. Thus, we have to have a converging lens. So the second type of lens is going to be converging or convex because we know we're producing this image on the screen. So I've drawn out that convex lens. Now, let's take careful stock of the information we've been given about all the distances involved. We've been told that the object is 20 centimeters away from the first lens, but we've also been told that the object is 110 centimeters from the screen. I'm going to draw that here. Alright, so what can we do first? Well, we can analyze what's going to be produced by that first lens. We've been given a focal length, and we've been given a height and a distance away. That's all we need. So let's find the image by the first lens, and then we'll consider the overall magnification. Those are two things we can do right away. So find the image produced by the first lens. We're going to assume that we are dealing with thin lenses, so we can apply the thin lens equation. So it's 1 over our S1 for the first lens plus 1 over S primed of the first lens, so our distance to the image, and then equal to 1 over F1. Okay, so we know that our S1 is 20 centimeters, and we don't know our S prime, the distance to the image. We'll find that. And we also do know our F value. So that's negative 20. Okay, so if we look at this, we can rearrange for our value of S prime, and we get negative 10 centimeters. Alright, so now that we know the distance to that first image, first of all, we see this negative, which means that it's on the same side as the original object, which is not surprising because we have a diverging lens. And we can draw this roughly out. I'm not going to do a complete ray tracing diagram here. I haven't done this really carefully to scale, but if you draw that one of these lines that goes straight through the middle of the lens, we can get a pretty good sense, because we've calculated the distance to the image, right? And that was half this distance. That was 10 centimeters. So that's our S prime one is 10 centimeters. So we know where it is, and so we can draw this out approximately. So let's grab onto our tree, make a copy. And we see already it's going to shrink down. So we're going to have this image right about there. I really don't want it to be angled. I think that's confusing. So maybe I'll try this again, try not to angle it. So we're about halfway between the lens and the object, and it does look like it's probably about half the size, just based on that. Okay, I'm just going to draw, forgot to put a little arrow. Okay, so I'll put a little arrow on the other side as well. But you can do a proper ray tracing assessment here and do this really precisely. Okay, so now what else do we know? Well, we've been told that the image produced is going to be 2 centimeters tall. Okay, so we know what the overall magnification is going to be. We have a big M, we'll call the overall magnification big M. That's going to be equal to, it's going to be double. And we can look at this and also know that if we have an upright object to the left of these lenses, well, that is going to give us an inverted image on the other side, because we're going through this convex lens, so an upright image on the left. So we're going to, this is our object for the second lens. That's going to go through the convex lens, and that is going to produce an image that is inverted. So we know, and let's maybe even just pull this over, because now we know enough that we can do that. So let's duplicate that. We're going to bring it all over, and we're going to make it twice as big and flip it. So it'll be something, I think that's about twice as big. Let's take a look. Pretty close. Because at this point, we know the overall magnification, the absolute value of the magnification is 2, because we were told what the height was. It's 2 centimeters. And because of the lens that we're using here, we know it's inverted. Okay, so we're starting to piece this together. So our magnification is going to be equal to -2, but we also know that that is equal to the combination of M1 and M2. Well, what are those? We don't have the information for 2 yet. We're going to use this analysis to get there, but we can find M1. Okay, so how do we find M1? Well, we're going to look at that ratio between the distances. right, so we have negative 10 centimeters all over, that was 20 centimeters. So we get an M1 value of 1/2. And that looks about right. Okay, so we've got, so now we actually know what the height is there. So the height of that kind of first image is going to be equal to 1/2 centimeter. Okay, so we know that our overall magnification is equal to -2, and let's actually just solve for M2. So that's our big M divided by our M1, that's -2 divided by 1/2. And so we now know that the magnification provided by that second lens has to be -4. That's helpful. Okay, so what then can we use this to do? Well, we're going to get a relationship between the distances of the object and the image for the second lens, because M2, maybe I'll just divide this out a little bit, keep this organized. Because we know that M2, which we found, is going to be also the ratio of those distances. M2 is equal to -S2 prime over S2. And so that all is equal to -4. And so now we know there's a relationship between S2 prime, which is equal to 4S2. All right, so what do we do with that? It's an expression rather than giving us a value. Well, what else do we know about these distances? Well, let's go back up to our diagram and take a look. What do we know? Well, let's draw those distances out. Maybe I'll do them in a slightly different color. So here we've got the distance from the second lens to the image. And so that's S2 prime. We can also draw out the distance from that lens to the object. And that's S2. We also know that that whole length is going to be 100 centimeters, because we know that the distance from the screen to the original object is 110 centimeters, and then the distance from the original object to that first image is going to be 10 centimeters. And so the remainder is 100 centimeters. So this also gives us a relationship between these two values. Just to make that connection a little clearer, I'm going to keep it in that color just the first time I write it. So we also know that S2 plus S2 prime is equal to 100 centimeters. And now we can combine these two equations. So I'm going to substitute in for S2 prime for S2. So I'll have S2 plus 4S2 is equal to 100 centimeters. And so that means that 5S2 is equal to 100 centimeters. And that means that S2 is 20 centimeters. All right, so S2 is 20 centimeters. And that means that S2 primed is going to be 80 centimeters. All right, so now we know basically everything except for that focal length of that second equation. And so now let's just separate this off, keep it all organized. Now we can go ahead and calculate the focal length of that second lens. Well, we can use our thin lens equation again. So we've got 1 over S2 plus 1 over S2 primed is equal to 1 over F2. And so that is going to enable us to say, well, okay, let's try and put it over to the side. So 1 over F2 is going to be then equal to 1 over 20 centimeters plus 1 over 80 centimeters. And so that gives us an F2 value that's equal to 16 centimeters. All right, so we know the focal length of the second lens. And what else? Were we asked for anything else? Let's just verify we've done everything. So what are the focal length? Okay, we've got that. And the distance from the screen, well, we've got that, of the second lens that will produce a well-focused 2 centimeter tall image. Okay, we've got everything. And so we're good. So that is how we analyze that 2-lens system. And really, the key to most of these problems is to remember to use, a step-by-step approach where we can do the analysis as usual with one lens, and then we follow through with the second lens using the image of the first as the object for the second. And that's it.